In this video, we're going to be um, going over an example of circuit analysis and how to analyze the voltages and currents that are going through basic circuits. So I've drawn a circuit here. I know some people in this class have not taken, I think, any electrical engineering or any circuits class before, so I'll be pretty explicit about what I've drawn. So this element right here, we're going to call a voltage source. And this voltage source, in reality, it could be a battery, could be some sort of outlet. It's a source of a voltage, and as we discussed in previous videos, voltage is an electrical. It's a potential. It's kind of a pressure that makes things move in an electrical system, and so it provides some voltage V in into the system. So similar to a force or a torque in mechanical systems. Here we have a resistor, um, and the resistance is measured in ohms, which is usually given the symbol of a capital omega. And here, this is a capacitor. And the units of a capacitor are farads, which are denoted by a capital F, usually. Um, and so if we think about current as the flow of electricity or the flow of electrons in a system, a resistor is something that restricts current. So if you think about a pipe, it's like a pinch in the pipe um, that allows the pressure or the voltage to change on either side. And also, and the degree of pinching that you get in that pipe is going to be measured by the ohms or the resistance of the resistor. A capacitor is going to be something like a tank, where if you have flow coming in, you have some sort of tank, and then you can have flow going out. And what it's going to do is it's going to delay the system. It's going to also store some voltage. So as flow comes in here, you have to fill all this part up before it starts to come out the side. So it adds some delay and uh, some storage, energy storage into the system. Um, this symbol is for ground, and that serves as a reference voltage, so V equals 0. Voltage can be thought of similar to height in mechanical systems, where it doesn't matter if height is measured from the ground that you're standing on, or the top of a table, or the third story of a building, or sea level. You just need to pick a 0 and stick with it. And voltage is the same way. You need to pick a value of voltage that is 0, and all of your measures of voltage need to be made in reference to that. And that's the purpose that ground serves in this circuit. And so we're going to apply a Kirchhoff's current law to the system. That means that if I draw current going into this node right here, and I call that IR, and I draw current going out, IC, that means that IR, the current going in, minus IC, the current going out, is equal to 0. That means that IR is equal to IC. And so now we'll use some of the relationships that we discussed in previous videos to um, make to make some sense and to make use of this equation. So the IR, the current flowing through a resistor, is going to equal the voltage drop over the resistor. So V in is the voltage right here, and V out is the voltage on the other side. So it's going to be V in minus V out over the resistance. IC is going to be equal to the capacitance times the derivative of voltage, or the derivative of the change in voltage. So it would be V out dot minus the voltage over here is 0, so the derivative is 0. which is 0. So IC is just equal to C V out dot. So now I can plug in IR and IC back into our equation. So V in minus V out over R is equal to C times V out dot. And in this case, V in is serving as an input, an inhomogeneous term, and V out is our variable of interest, our dependent variable. So what I'm going to do is I'm going to move all of the V outs to the left-hand side of the equation, and all of our V ins, the V in to the left or right-hand side of the equation. So I've got something like minus C V out minus V out, or V out dot over R equals minus V in over R. I'll go ahead and I'll get rid of the minus signs and I'll multiply by R so I don't have any fractions to deal with. So I've got RC V out dot plus V out equals V in. And so this is a linear, first order, inhomogeneous, constant coefficient ODE. And we can start to think about it the same way that we've been thinking about these equations for mechanical systems. So if we remember, for mechanical systems, we can write a first order linear ODE as tau x dot plus x equals f of t, and that time constant tau is or that tau is the time constant. It measures how long it takes to maybe decay to 37 or by 37% to 37% of your initial value. If you're dealing with a step response, then it measures how long it takes to get 63% of the way to your system or to your final state. And in our case, tau equals R times C. Um, so I hope that we're starting to see some of the relationships and how some of these systems, electrical systems like this one, look very similar in this case to a first order mass damper system. So we'll go ahead and stop that video there.